Okay, I think we've started streaming. So I'll give people a chance to come in. I've set this up a while back. You can see it says waiting for Salt and Science. I set up it 40 minutes ago, just been tweaking a few things. Hopefully it started streaming. I'll be checking on my iPad with a bit of a delay. And then we'll make a start. So just give people a chance to come in. I will try and trim this video to start when I properly start speaking. Let me just get my iPad here. It looks like we are up and running. Yes, we are. Okay, so we got a few people in. 5 people. One of them's my iPad, which I'm going to mute now. Good. So we started. We're streaming. We have a lot to cover today. So I'll just give people a chance to come in, and then we will get stuck into it. But what I have noticed is, even a little trawl through YouTube tonight, there is a lot of people, a lot of teachers in the same position as myself doing physics paper 1 revision sessions. So it's quite interesting seeing all of the possible things you can look at. I like to think of it as walking into a bookshop and seeing 1,000 books on the same subject. Which one do you pick? Well, it's totally up to you. Sometimes it's the one that's got the nicest covers. Maybe it's the one that has the prettiest pictures, or the one that has the strange Scottish person narrating it. It's totally up to you. So I'm not here to say, join this one, this is the best one. It's just, I'm trying to help. Okay, so if I can help you tonight with some things before tomorrow. How long will it take? When's kickoff? All right, I do want to watch the football at some point, but also I appreciate you have an exam in the morning, so you need some help. So my point tonight is I can't cover everything. I've put a few little links in the chat information which you can download and look at. So tonight is all about anything I can do to help. Maybe give a little insight, maybe little tweaks, little hints, little nuggets of information that might help you tomorrow in the exam. So just to make you aware, yesterday I recorded, as my papers just go flying, let me go to my browser. So I recorded yesterday, not this thing, I recorded this. So I did a whole sort of hour-long little lesson on electric circuits, because there is quite a tricky concept. So I've done this, which you can watch at your leisure. If you're stuck with circuits, you can have a look at this. It's definitions, it's equations, it's how circuits work. So I strongly recommend this is all about circuits. Tonight I don't want to focus too much on the circuits. We're going to focus on energy, density, and a little bit of radiation. So that's kind of a separate one, which is on the Salt and Science channel. Now let's go back to this. So let's begin here then. Okay, let's begin with energy stores. You have to know the 8 energy stores. There they are on the screen. Some of these I put down POT for potential. This is chemical potential, nuclear. So actually most of these are potentials other than kinetic. Okay, or thermal. I would say thermal is a sort of a special version of kinetic in terms of particles. So energy is either something that is happening or something that is about to happen. And there's one thing I want to stress right at the start, and something I noticed, and my sort of fellow teachers have noticed this in AQA mark schemes. They really want you to mention this word work. Okay, we'll try and use it a lot tonight, but if you can think in your revision, where can I use the word work? Okay, if friction does work against the motion of a car, if it's doing work against gravity when you lift an object up, the idea of work is something that you should look to include in your energy answers wherever possible. So here's the 8 stores. There is the 4 pathways. A couple of little hints for the pathways. A mechanical pathway is always going to be a force. Electrical is going to be current. So looking back to my video yesterday, that's charge moving in a circuit, transferring energy from one location to another. Heating is going to be conduction. and that's when you have one substance transferring heat to another substance. So it's by direct contact. It's the particles of one substance which pass on energy to the particles of another substance. And radiation is emerging out from a heat source. So, for example, everyone radiates out thermal energy in the form of infrared, electromagnetic radiation, which travels at the speed of light. It can travel through a vacuum, and you can pick up that heat at a certain distance, which decreases with distance. Heating is when you're in direct contact with air or a liquid or a solid. So just be aware of some examples. Some textbooks say that light is in the radiation bracket, which it is. Sometimes they say so is sound. Now I would argue sound is more mechanical because it's particles of air in substances moving back and forward, forcing other particles to move, but that's a detail. Okay, let's not dwell too much on the examples. One thing you have to know is why I put them in this order is because these four here carry with them equations. Now I'm going to show you the equation sheet you'll get tomorrow shortly, but let's just have a little check as to what these equations actually are, so you recognize them in the equation sheet. Kinetic energy is, of course, E small k is 1/2 mv squared. We only square the speed. Gravitational energy is E small p as mgh. Elastic potential is E small e, which is 1/2, looks very similar to this one, ke squared. May I recommend that along with this one you know the companion equation, which is k is equal to F over E. So that's going to be the force to stretch or compress a spring divided by the extension gives you how strong the spring is, the spring constant. And this is measured in units of newtons per meter. It's an indication of the strength of a spring. Now thermal energy, this is tricky. So thermal energy actually comes in two forms. Okay, now I'm going to just stress this now. Whenever you give thermal energy to a substance or you remove it from a substance, then you're going to increase its temperature or decrease its temperature. Okay, and so you either change the temperature by increasing it or decreasing. If you add energy, you're going to increase the temperature. If you remove it, you decrease the temperature. Or if you add energy to a substance and you get it up to its melting or its boiling point, you can change state. And it's never both. Never both at the same time. It's either one or the other. So if you're changing temperature, you're not changing states. If you're changing state, you're not changing temperature. And you have to identify the two equations. So let's so I think what we'll do is, if you want to turn off the chat yourself, you're more than welcome to. I think obviously as much trust as I put in people to be mature, I think YouTube live chats are a sort of there's parallels in society where I'm afraid you just have to put up with idiots. The idiots are around us everywhere, and we have to cope with idiots being in life. We do our best to ignore it. So if you want to turn off the chat, please do so. If you want to ask me a question, then please use the chat for that purpose. But again, you know, we can't stop people being who they are. It'd be nice to be mature and have a good revision session, but I know I'm asking a lot, and for some people. Anyway, yeah, I don't want to turn off the chat just because people are asking questions. Right, let's go to number 5 on here. Yes, this one here, which is the equation sheet, which you will get tomorrow. Okay, so in the same way as you get an insert into the chemistry paper, which is the periodic table, you're also going to get, tomorrow you get an equation sheet and an insert in the paper. Now it says trilogy, which is combined science. Now you notice the equation I've written already, which is the top 3. That's handy. The next one down, this delta E, which is change in energy, is mc delta theta Now that looks like a proper equation. It looks complicated. Okay, there's a Greek letter in there, but there's a couple of Greek letters, delta. So we need to tackle that one. If you scroll down to the next page, you'll see another one called thermal energy for change of state, which is E is equal to mL. So these two are ones which correspond to, let me just go to my software and then we just switch back to there. So change in state, change in temperature, we've got this delta E is equal to m times c times delta theta, and then this one here is E is equal to mL. We can tackle the C and L at some point tonight because it will come up tomorrow. Question: would I have to use 23 equations? No. Okay, they're given to you all, and you have to know. Sometimes you'll be asked a question: what's the relationship between current, potential difference, and resistance? It will always give you the three things or the parts of the equation in alphabetical order. So it won't necessarily be in the order of the equation. For example, this one here, it might say what's the relationship between energy or thermal energy, mass, and specific latent heat as E equals mL. So you get away with writing down the letters now. It used to be you had to write down the words, but now in the question it'll give you the things in the equation in brackets with the symbol letters. So you just write down the equation, you get a mark for that. They still give you those questions even though you're going to get the equation sheet. So we need to have a look at how we use these equations. Okay, so we'll do that in a bit. You also have to be aware of transfers of energy. Now there's a big concept in the universe which states that energy cannot be created or destroyed. It's called the conservation of energy. And it has huge implications, and we'll discuss one which I think is going to come up tomorrow. But before we get that, we need to look at transfers, or moving from one store to another. So if we look at a car, and a car is driving along the roads, and what's the energy transfers taking place? Well, the car has fuel in it. So the energy for the car to move is going to come from the chemical potential stores of the fuel through the combustion engine. That's going to transfer to movement of the car, which is going to be kinetic. So far so good. But what if the car suddenly went uphill? So as the car is moving, it's doing chemical potential to kinetic. As it goes uphill, it's going to also convert that to gravitational potential. Now hopefully you see all the energy from the chemical potential, when it's going flat, goes into kinetic. When it starts to go up the hill, we have to compromise and use some of this energy to do work against gravity. Okay, so we might not be going as fast, so you might slow down as you go up the hill. I'll put a link in the description to a little animation where you can play with a skateboarder going up and down a ramp. But there's also one thing else to consider, which is energy loss. Okay, so every transfer of energy, we're going to have some energy wasted as thermal. And it's usually wasted, we say, to the surroundings. Okay, and that's due to friction. Friction in the engine, friction between the tires and the road, friction between the car moving in the air, so air resistance. So not all the energy from here is going to be seen as kinetic energy, and so we have to think about efficiency. So efficiency is useful energy out divided by total energy in. That equation will be given to you. This will come out as a decimal. So between 0 and 1. If it asks for a percentage, you just multiply by 100 to get up to the percentage. But the equation relies on being used with a decimal. So here's one for you. If you're given an equation to work out efficiency and it says, or to work out useful output, so say it says the efficiency is 75%, you're going to change that immediately into 0.75 because only the decimal works in the equation. So just a little throwaway just to add into your consideration. This is transfers of energy. Now I want to show you a little video clip from YouTube. I don't know if I'm allowed to, but we'll give it a go anyway. So I'm going to go to my browser and I want to go to here, and I want to just switch to in fact, let's go to this one first of all. This is a Lamborghini, and I want to see, and here I want to show you how the kinetic energy under braking transfers, or so the brakes do work. So the brakes are going to cause friction as you squeeze the brake. So work is done by friction, and what happens is that energy is released as thermal energy to the surroundings. And you see there that the brake discs are glowing red hot. So you can definitely see there that the kinetic energy is being transferred into thermal energy because the friction of the brakes are doing work. And that heat energy comes out as, you see the brakes are glowing, so that's thermal energy being radiated out and conducted out to the surrounding air. So it's wasted energy. It's quite cool. Let's show another one really quickly. I've been showing this video for years. This is a roller coaster in New Jersey. It's called King Dakar. Now there's a massive big catapult at the very start, which means that that's a huge amount of elastic energy. Okay, so elastic energy at the very start, and then that will translate as it launches the roller coaster, it converts into kinetic energy. So I'm going to narrate it as we go along. So it goes elastic energy to kinetic energy, all kinetic now, up to power. When we lose kinetic energy as we're doing gravitation, we work against gravity over the top with slow speeds. Let gravity do the work now and pull you down to the ground as you gain kinetic energy as you lose gravitational. Listen for the brakes at the end. There, that's a friction sound, that's the brakes doing work and slowing down the roller coaster. So kinetic energy converted to thermal energies, just like the brakes of the car, the Lamborghini. So back to this then. Let's think about another idea of this conservation of energy. Let's think about falling objects. And I guarantee this will come up tomorrow. It's kind of grown in favour somewhat, whereby they ask questions about falling objects. So let's consider an object up high. It's going to roll down to there. Okay, and let's give this, let's give it a height, or what should we give it? I did have some questions here. Yes, I did. So we are going to have, let's see, where's my questions? Let's do, bear with me for a second. Okay, we jump straight in. If I'm just do this one here, and I'll come back to that in a second. So we've got a question here. A large rock of mass 20 kilograms is hoisted by a crane to height 25 meters. What's the gravitational potential energy at this height? This might be an example of a question you may face tomorrow. And really simply, we know that the equation is EP. I'm just going to get rid of this paper here in case it goes, oh, I'm fine. Sorry guys, just squaring this up. So EP is equal to mgh. It may tell you the G value, unless it says otherwise. Use 9.8 because we're on that's the gravitational field strength and the surface, or just above the surface of the Earth. We get 20 kilograms, sorry, for the mass. We've got G is 9.8, and the height is 25 meters, and that gives us a number. That's 4,900 joules. Then we're told that the rock is dropped. what would the speed be just before impact with the ground? Now, I guarantee this comes up tomorrow in some form. It could be a big 5-mark, 6-mark sort of numerical question. The skill to work out the speed at the bottom relies on a big concept, which is called the conservation of energy. So I'll move this just now, and we should know that the gravitational energy at the top is the same as the kinetic energy at the bottom. That's assuming that we don't have any loss due to friction in terms of wasted heat energy. So we should know that mgh up here is the same as a half mv squared down there. It's the same value. So whenever you do these questions here, so this one here, we have to state our assumption, which is EP at the top equals EK at the bottom, which is equal to 4,900 joules. We're stating that assumption. That's our assumption. And then if we know the value for kinetic energy and we know the mass, we can work out the speed. But it's a little bit trickier, so let me just take you through the steps. We've got the equation, which is EK is equal to 1/2 mv squared. We know the values for this one. We're trying to find v. So we've got 4,900 is equal, now the half fraction we write it as 0.5. 0.5 times 20 for the mass times v squared. And we get down, if we do the maths here, so that's going to be 0.5 times 20 is 10. Take the 10 across, it's going to be 490 is equal to v squared. And we do the reverse operation of this to get the on both sides. So we square root both sides, and we find that v is equal to the square root of 490, which is 22.14 meters per second. Okay, I think this will come up tomorrow because it's come up in the last few years, and it seems to be quite a fashionable question. Good question, Daniel. 9.8 is Earth's G value. It's 9.8 newtons per kilogram. It may give you that in the question. However, unless you're told what planet you're on or to use a certain value, just assume you're in planet Earth, in which case G is 9.8. It's a really good assumption and a number to get into your head. So that's where that comes from. It's the gravitational field strength of Earth. But please, please, please have a look at how I've done that. Even pause this later on and see how we do the working. Okay, it's all to do with conservation of energy. I won't do this question here because I need to move on into other things. What I'll do is I'll try and put these questions with answers on in the description, as my dog barks in the background there. So this is a good concept to have. Sorry, my dog is barking at another dog, which is about a mile away outside, as he often does. Hold on. Okay, so let's move on then, and let's think about heat. Okay, let's think about this idea of changing temperature and changing state. Just get a fresh bit of paper. All right then. So we've got these two equations. So we've got this delta E is equal to mc delta theta, and then we've got this E is equal to ml. Now these constants, this one here is called specific heat capacity, and as a definition, it is the energy required to raise or change 1 kilogram by 1 degree Celsius. For example, water has a C value of approximately 4,200 joules per kilogram degrees Celsius. In other words, if I want to get a kilogram of water and increase its temperature by 1 degree, then I've got to use 4,200 joules of energy. If I want to raise 2 kilograms by 1 degree, then I've got to use 2 times 1 times this. So it's going to be 8,400. So this equation essentially just says, what's your mass in kilograms? What's your temperature change? So this delta theta is your energy change. And that's going to be in degrees Celsius. This is your mass in kilograms. And this is your energy in joules. And so you may be asked, here's an interesting question. You may be given the energy of something, of the energy transferred. Remember, if you remove it, you cool it down. If you apply it, you heat it up. You may be given the mass. You may be given the C value for a substance. You're asked to work out the temperature change. Sometimes it says what's the final temperature. So you might be given an initial temperature. You calculate the delta theta, the change, and you have to work out the new temperature. So be careful, read the question carefully whenever it discusses this equation. This one here is just, this is mass again, and this is energy, but this L value is specific latent heat, and there are two versions. There's fusion, which involves solids to liquids, or liquids don't. If we add energy, this is the energy required to change state. So I should write it down actually as well. This is change state, and this is change temperature. Remember, never at the same time. So the value for L of fusion is when you melt something or you freeze something. If you add heat, you melt it. If you remove heat, you freeze it. Or you've also got vaporization, which is liquids to gas or gas back to liquid. Okay, so you'll be given this value. It's measured in joules per kilogram. My recommendation is to look up some examples of how these questions are used. Every paper one will always have one of these in it. So I recommend looking these up. Okay, and again, the catch is if you're working at a final temperature and it relies on you working at delta theta, you have to add it on to the end or subtract it, one of the two. This one is all about changing state. So it might say how much energy is required to fully boil a certain mass of water. You choose that you'll be given the L value, you apply the mass to work out the energy required. Okay, they look complicated, they're not that complicated. All right, you've got to do some revision on this stuff, but that's my little top tip there about delta theta. Now let's have a think also about another aspect of energy, which is energy resources. And I'm going to tie this into a little bit of electricity as well. So let's just change paper. You need to know the energy resources. You need to know about renewable and non-renewable. So this is energy resources, and we've got non-renewable and then renewable. I strongly recommend knowing some of the technologies, at least which belongs to which list, and then perhaps knowing some of the technologies or some of the key facts about some renewables. But non-renewables, again, a key word you want to include in this is going to be the fuel, or the source is finite, which means it will run out. And we've got our fossil fuels of coal, oil, and natural gas. These are our fossil fuels. We've also got nuclear in here. Nuclear, it involves uranium as a fuel. And curiously, you actually get between 2 to 5 million times more energy output from a kilogram of uranium fuel than you would from a kilogram of coal. So it's very, very high energy output, but it's very expensive. So I recommend knowing a few advantages and disadvantages. Nuclear is low polluting, but very, very low polluting gases. But the problem is nuclear fuel has to be disposed of, and we'll discuss a little bit on radiation towards the end. You've got to know that most of these, or all of these, emit CO2 as pollution. Okay, so these are all CO2, which is a greenhouse gas. Coal will also emit sulfur dioxide, which dissolves in the moisture in the air and falls as acid rain. So you need to know CO2 is a polluting gas. Please don't write environmentally friendly. Stick to the science language. So it's polluting gases like CO2 or CO2 and SO2. And these gases are either greenhouse gases or can cause acid rain, which can damage wildlife and limestone buildings. Don't just say it's environmentally friendly. That's not going to cut it, I'm afraid. Using language, greenhouse gases are polluting gases which can lead or cause climate change. The greenhouse effect, which you cover in paper 2 chemistry, is actually good. The problem is that we are upsetting, or we are adding additional CO2 to that fine balance. The greenhouse effect is good, but we're making it too good. Renewable would be, so the question there, yep, thank you. The renewable is, it can be used again. The fuel that we use or the method we use can be used repeatedly. And we've got the classic examples of wind, we've got solar, we've got biomass, we've got hydroelectric. What else have we got? We've got tidal. So these are some sort of geothermal as well. For example, a lot of Iceland is powered by geothermal. They're very lucky for the geography. So we need to know some advantages and disadvantages. These two in particular are heavily dependent on weather. Okay, biomass is considered sort of better for the environment in terms of the CO2 that it produces was actually, because you are you're burning biological material which itself took in carbon from the atmosphere, it's seen as a smaller carbon footprint. Again, that's something you might want to mention. Hydroelectric is when you build a dam in a river valley and you block the river, the water builds up behind. It's called a reservoir, and the water can fall from high to low. So essentially you have water behind the dam, you get a big dam here, you get the river down there, and the water falls from here down to there, and as it falls it turns a big turbine, so you have EP to EK. Now most of these sources of energy, with the exception of probably solar, so all of these energies apart from solar will involve trying to turn a turbine. So you've got a massive big huge rotating coil of wire or magnet, and you try and rotate that around some wires, and that, so basically any way we can get to make this rotate. Okay, so whenever you burn this stuff over here, you're trying to get heat, and that heat turns water to steam, and that steam can be funneled along pipes and can get through the propeller blades of a turbine to make it rotate. So you're trying to rotate a big huge magnet or a big huge set of coil of wires against a magnet or coil of wires to generate electricity, but it's got to be some kind of energy to get it to turn. For wind, it would be directly using the wind to turn the turbines. Solar is mostly used for heating up water in the home. It's a good way to get that. But these are all, hydroelectric is falling water turns a turbine. Biomass is producing heat again to turn water to steam. Tidal is when the tide moves in and out, and as it falls back down it can rotate a turbine. Geothermal, again, heat, you turn a turbine. So, again, those are renewable, non-renewable, and all of this is for, let's do a little bit of electricity. This is the question there. Okay, Newton's laws are in paper 2. Okay, so you need to worry about Newton's laws just now. They are in paper 2. So, these are all effectively power stations. And power stations are the sort of the source of energy in the national grid. So you have to know what the national grid is. Okay, the national grid is a network of power stations. Okay, and those power stations, the electricity that you make when you turn the big turbines, that goes into a transformer. So we get power stations. We've got a transformer, and this was called a step up transformer, and that goes into these power lines. And you might see these large structures that sort of line motorways or over landscapes. These are the power lines. So power lines or transmission cables. And then from here they go into another box, and this one's called a step down transformer, and then it goes into sort of domestic use into the homes. So factories, buildings, offices, homes, schools. So key things are, you get step up, you get step down. And the idea here is, in a transformer they must use AC. Okay, so these are electromagnetic devices. They involve they basically involve generating magnetic fields in a coil, which induces a secondary voltage on this side. So these are, again, you don't have to know this for combined, it's a triple paper 2 stuff, but you have to know they only work with AC, they don't work with direct current. That's why AC electricity, so my pen flies off, so AC electricity is for domestic. AC, because the national grid relies on step up, step down transformers, which only work with AC electricity. Now these power lines, I think the values are around about, I think it's something like 25,000 volts coming at power station. Transmission lines or transmission cables are 400,000 volts. And then we step it down, and in our homes we have approximately 230 volts. So we have lots of voltage, we step it up, we step it down into our homes. Now here we have, ideally, a really efficient power transfer. Now if you look at my electricity video, power lines, pylons. So pylons are the metal things. In fact, pylons are the bits that hold the cables. The metal things have a different name, but we just call these pylons. Yeah, the transmission cables are up there. In the winter time they're quite straight. In the summer they're quite saggy because the metal expands. So they droop down in the summer. That's why they're up quite high. So when they droop in the hot weather, they don't droop too low, and you touch them. Basically, if you stand here, okay, and you were to touch this, the high voltage will produce a current through you to the ground. So that's why they're up really high. You don't want to go anywhere near them. Okay, there's huge dangers with going anywhere near these lines. Now, they're 400,000 volts, but they're also low current. Now, the lower the current, the less heat is lost. So we're going to use this equation here, which is on my other video. If this is low, then there's low heat loss. Okay, so the voltage is really high and the current goes really low. And if we look at the power and this power line here, which is this P, if the current's really low and the resistance of the wire is reasonably low, not super low, but reasonably low, then we have low heat loss in the power cable, the power line. Now in a transformer, it's all to do with power before, power afterwards. I'll do a really quick bit down here. So power, remember, is V times I. We want to have the V times I on this side. We'll call this primary is equal to the V times I on this side, which is secondary. And essentially, if the voltage goes up, the current has to go down. Okay, so if this is 25,000 volts and a reasonable current, this voltage goes up high, this must go down low to keep it balanced. So that's why we have low current in these lines. But the national grid, you have to know that power stations, transformers, power lines, and end consumers. It's the network of all these things. Okay, let's, when it comes to domestic electricity, look up plugs. Okay, look up plugs and look up your, it's 50 hertz. Again, okay, just a quick one. There was a question, a good question came up there. If we look at the voltage, the voltage here is actually AC, so it does this. Which means the electrons, the charges in the circuit are moving one way, then the other, then the other, then the other. And it's 50 hertz. Yeah, it's a good point actually. Thank you for asking the question. That's usually a little fact that comes up. You have to know it. It's 50 hertz. The reason for it is just that it's the best frequency efficiently transferring energy in the national grids. But remember, why we have AC is because these important transformers only work with AC. Okay, they don't work with direct current. Now let's move on to something which I do think will definitely come up. Okay, let's look at density. Okay, let's look at density. Now, there is a required practical, and I think it will come up tomorrow. But density has an equation. It is mass over volume. That's the symbol rho, which stands for density. And we use kilograms and meters cubed. But I've noticed occasionally it comes up, we've got grams and centimeters cubed. Sometimes, you know, these are the SI units, but they might chuck that in there, say, okay, what are the units in grams per cubic centimeter? But let's just figure out what density is. It is essentially how much stuff you've got and how much volume. Okay, that's it, essentially. And so the density of water is 1,000 kilograms for every cubic meter. So let's have a little chat about volume first of all. A cubic centimeter of anything is 1 by 1 by 1. So it's 1 by 1 by 1 centimeter. Okay, it's a cube. A cubic meter is going to be 100 times. Obviously this is not to scale, otherwise my paper is going to be huge. So we've got 1 meter by 1 meter by 1 meter, and that is a 1 meter cubed. That's 1 centimeter cubed, that's 1 meter cubed. Now, the conversion is pretty tricky, okay, because there are 100 this way, and 100 this way, and 100 this way, so that's actually 1,000,000 times bigger. So there are 1,000,000 of these in a cubic centimeter. So let's have a little glance at this for a minute. I'm going to show you these questions shortly, but we need to know that it's too small. It's fine. In terms of liquids, 1 milliliter of water is the same as 1 centimeter cubed of water. You need to know that. You've also got to know that to do this conversion, there is 1,000,000 centimeters cubed and 1 meter cubed. And so you have to do, if you're given a volume in centimeters cubed, you've got to do the conversion, you've got to divide by 1,000,000 to get into meters cubed. So you've got to be confident doing this, and it's not even though a centimetre to a metre is 100 times smaller, because it's 100 times 100 times 100, it's 1,000,000 times the volume. Okay, so let's have a think about density then. Now we need to discuss the required practical. Okay, and the required practical, it basically says calculate density, and there are two parts. Okay, there's regular, and there, excuse the dot there, and there's irregular. Okay, irregular shapes and irregular shapes. And the regular shape might be something like a cube or a cuboid. So we've got our shape here. And the irregular shape could be a rock like that. The story goes that Archimedes was challenged by the king of Greece to verify if the crown makers had swindled him out of gold, and he wanted to know if the crown that was made for him was made from pure gold and not cheaper metals with gold plated. And so the problem was to find out the volume. And so let's discover the volume today. Let's figure this out in terms of the practical. So to know the density, we've got to know mass and volume. So to work out the mass of a regular object, okay, we use a thing called a spring balance. Avoid writing scales. Okay, use a spring balance or a top pan balance. Spring balance is a good thing to say. To work out the volume of a regular shape, we use maths. Easy as that. We use an equation. Okay, length times width times height. If it's a sphere, 4/3 pi r cubed, whatever. So we use maths to work out the volume. You have to measure the lengths, but we use maths. And then density, we just work out by doing mass over volume. Dead easy. That's easy. We just use maths and measure the length. For irregular shapes, well, to measure the mass of this one, surprise, surprise, we use a spring balance. Now this is the bit that gets a little bit tricky. For the volume, this is the descriptive part that you have to know. We use something called a Eureka can. Well, there's various methods, but let me show you the way I would do it. You have a Eureka can, which has this spout, and then you fill the Eureka can with water up to the level there, and let any excess water spill out. You would then place the irregular shaped object in the Eureka can. Okay, let's place the object in the water, and then the water level will rise up. As it rises up, it pours out, and your job is to measure accurately using a piece of apparatus with a resolution that's suitable. This could be a measuring cylinder, and so the displaced water equals the object volume. So the key phrase there is displaced water, or water displacement. So the object goes in, water is displaced, and excess water is collected and measured with a higher resolution piece of apparatus. Measuring cylinder, you might want to mention that. Now there is a way to do this with just a measuring cylinder, which means that you have water up to a certain level. If you have one big enough, you can put the object into the measuring cylinder, and then water will be displaced. So any additional rise in water is due to the object's volume. But the key phrase here has got to be, you've got to mention this, is displaced water or water displacement. You can't get away with doing without saying that phrase. Would you ever need to work out the, let me just check this on the chat, how much an object weighs when suspended in the water? Not, Fred, not for combined. For triple, yes. That's to do with the buoyancy force pushing up from the object in water. So the weight will pull it down. You have buoyancy pushing up, and that causes a decrease in any weight, any apparent weight. But not for combined. You're okay for combined. But this, I think this will come up. Oh, and the last thing is density is equal to mass divided by volume. So you have to mention the equation you use at the end. So this would be 4 marks. Okay, 1 mark for saying spring balance, 2 marks for saying the apparatus you use. This is called a Eureka can, in honor of Archimedes' principle. You must mention displaced water, and you have to mention a measuring cylinder and talk about the fact that the resolution of the measurements is enough or suitable for the question. Do you say it was ending at 8? Well, if that's the kickoff, then we'll try and end it soon. All right. We may go a little bit over, but again, if you want to go and watch the football, then you feel free to do that. You can watch the rest of it later on, pick it up after an hour. So that's the required practical for density. Here's just a couple of questions that that I made up a while back. Let's have a look at this one here, for example. So we've got the object in the Eureka can. We've collected this much water. So you'd have to read the value. We're reading 25 milliliters, which is 25 centimeters cubed of water. We would do the, let's see where my actual numbers are here. There we go. So you would do, for question 1 here, you would have 119.75 divide. Now this is 25. Now I've not drawn this perfectly. There should be a meniscus, which is that sort of lens type effect at the top of the water. So you measure to the bottom of the meniscus. Again, I should have thought about that. So this would be 25, and then that is going to give us 4.79. The units are grams per cubic centimeter. Now to convert between this unit and kilograms per cubic meter, times 1,000. So it's 4,790 kilograms per meter cubed. The reason being, you divide by 1,000 to go from grams to kilograms, but then you divide by 1,000,000 to go from centimeters to meters cubed. If you divide by a division of 1,000,000, you multiply by 1,000,000, add in 1,000. Anyway, it turns out to be you multiply by 1,000 to go from grams per centimeter cubed to kilograms per meter cubed. You multiply by 1,000. And the same you can do for these questions here. Okay, I've added these into the description. I've got my solutions here, so it's just repeating the process. Okay, now I think because of time, we're going to sort of wrap this up reasonably soon. Again, I've hit the major points I wanted to cover. I want to just go to my browser, which is there, and I want to just show you really quickly this. Okay, now this is important. This is to do with particles of gas. Okay, so I strongly recommend you stick around for this little bit, and then you can download my. Let me just find it here. You can download the summary for P4, and I'll show people where that is and how that works. So here we've got a gas, and I want you to notice that the particles of gas are moving in straight lines in random directions, and as they hit the walls of the container, they rebound at the same speeds. Okay, they don't lose energy, they lose a little bit. They don't lose energy as they bounce off the sides, but as they bounce off the sides, they apply a force to the container. So for the particles to bounce back, they must give a force to the container, and that's what we call gas pressure. If this was air, this would be air pressure pushing out. If you blow up a balloon, then the balloon maintains its shape because of the outward force of all these collisions with the walls of the balloon. But I want you to notice how in this animation, some particles are moving quickly, some are moving slowly. And so whenever it comes to this idea of, it's called the kinetic theory of gas, then you have to always talk about the average kinetic energy of the particles. The average kinetic energy is an indication of the temperature. So the particles have an average speed, they therefore have an average kinetic energy, which means they have a constant temperature. Now, what I can do is I can add a heater to the bottom of the container, and as a particle strikes the heater, it gets an injection of energy. So we are adding energy to the gas in the form of this conducting heater. So if you pick, I'm going to just reduce the numbers for a second so it's easier to pick out. I guess I'll let it reset it. So I want to pick out a slow moving blue particle. As it hits the container, it changes to red or to yellow. So it gets energy, so it moves faster, which means the overall temperature of the gas will increase. Even though we still get gases at random speeds, the average speed is now higher, which means the average kinetic energy is now higher, which means the temperature is now higher. And as these particles strike the sides of the container, because on average they're moving quicker, they'll strike with greater force, which means if we increase the temperature of the gases in the container, the pressure goes up. Now we can reduce. Now I'm going to just increase the molecule count again, just so it's a nice to look at. Okay, so I've just changed the simulation, not the actual gas. So we've got this heater going. If I raise the temperature of the heater, then every time the particles hit the heater, they get an even greater injection of energy. So the temperature increases with the gas. They're still moving at random speeds and random directions, so they're not all moving at the same speed, but the average speed has increased and the average kinetic energy has increased, so the temperature has also increased, which means as these particles strike the walls of the container, they strike with greater force, which means the pressure goes up. We haven't changed the area of the container, so an increase in force over the same area means the pressure increases. Now here's the cool thing. If I reduce the temperature, I'm going to go straight from heater to a cold surface. There we go. As particles strike the cold surface, they lose the energy to the cold surface. They release the energy or they give it up to the surface. And the overall temperature of the gas will reduce because the average speed of the particles decreases, the average kinetic energy decreases, the temperature decreases. If we left this for long enough, we might end up with the particles and the surface actually staying close together and forming a liquid, and that would be called condensation. So that's it. I wanted to show you that. It's quite cool. And obviously when I do this in class, I just go from cold surface to heater, 3, 2, 1, heat, and you have this sort of increase in temperature again because the average speed increases, the average kinetic energy increases, and the temperature increases, and therefore the particles striking the side of the container with greater force over the same area, pressure goes up. So that is something you have to know for tomorrow. And so just as a quick one here, here's 20 particles in each container. They're going to bounce off the sides. The force pushing this way is balanced by the force pushing this way. There's no overall change in, there's an equalizing force. Over here, you've got more particles here, fewer there. So this would produce less pressure in this direction. So there'd be a force this way in this barrier, and even greater force down here, because there's much less pressure here than there is here. So the gas in this container will be pushing on the surface, and this container might even burst the container. Here's a couple of comparisons. We've got 20 particles with a certain speed, or average speed, but when I inject heat into the system, they move on average with greater speed and greater velocity. They're going to bounce off the sides with greater force. That increases the pressure. So let's just capture some of those thoughts for a minute. You must mention the average speed of the particles. That informs us of the average kinetic energy of the particles. Again, these are all of the particles, okay? So I should just specify that, of particles, average kinetic energy of the particles, which tells us about the temperature. The temperature of the gas is a certain value, and that can also tell us about the pressure, because pressure is equal to force divided by area. So if we could think about a situation where it might say in the question for a fixed mass of gas, but let's just do that one because I've got a funny feeling it's going to come up tomorrow. I've got a really funny feeling. So let's just, I know it's past 8 o'clock, guys, but I want to just do a couple of things with you. So let's just think about a container of gas. So we get gas particles in there, all moving. And the question might be, what happens to the pressure? So the question might be, what happens to the pressure when the temperature increases? Okay, now you have to specify it's for a fixed mass of gas. In other words, we haven't changed the numbers of particles in here. It's a fixed mass of gas, or fixed number of particles. So what happens to the pressure when temperature increases? You have to make the connections. So now you would write yours out in words, obviously. Temperature up means that the average speed of the particles increases, which means the average kinetic energy of the particles increases. The force of collisions and frequency of collisions also increases. And the last thing you would say, for the same volume, then pressure is equal to force over area. If the force increases, if this is increasing and this is the same, then pressure increases. So let's just recap that one. You're making the connection between the temperature of the gas and the pressure. And the connection is, as the temperature increases, the average speed of the particles increases. As the average speed increases, so does the average kinetic energy of the particles increases. This means that the force of the collisions and the frequency of collisions increases. They bounce off the sides more and with greater force. And for the same volume of containers, the same area, the greater force over the same area means that your pressure increases. Now I've got a funny feeling that might come up as a longer question tomorrow. I don't know why. It's called the kinetic theory of gas. The same thing works if you have a decrease in temperature, everything's just reversed. Okay. Then they might ask you about volume change. The volume change would imply that the area changes, but that's something for you to revise if you find it on bite size or something. Now, the difference between combined science paper and triple science. For paper 1, there's only a few extra bits in electricity, like static electricity, and there's a few extra bits on this topic where we do pressure and volume, and there's a few bits on radiation, which involves nuclear chain reactions, fission and fusion. So there's not a huge amount. And I should just say, to get a 7 in combined science is just as difficult to get a 7 in triple science. Okay, it's the same standard of work. There might be more concepts, but the difficulty is the same. Okay, so there's no There's no demerit in doing the combined paper. It's just as hard. Okay, the challenges in how the questions are asked, the concepts might be more, but the challenges, the questions, and I think this is a challenging question that may be asked this in combined and triple. Now, just to finish, guys, I know time is pressing. Let's just quickly go to, I think it's number 5 on here. No, number 6. There we go. So just to finish off, I recommend that you have a look at this. I'll put a link to it in the description. This is going to go through the P4 radiation topic. I'm really annoyed because I was going to cover this question on Sunday night for chemistry, and I thought, no, it's usually reserved for physics, and the blooming thing came up. So this question was in the higher, I think it was in the higher paper for chemistry. I'm annoyed. It's the alpha scattering. So the way I've done this slide, folks, is I've got a question slide and then an answer slide. What was expected was the alphas to pass straight through because the gold atoms were sort of soft with the plum pudding electrons. What they found was that most passed through. Some were deflected, some were rebounded, or few were rebounded. But there's 3 consequences for this. Number 1 tells us that atoms are mostly empty space. Number 2, that atoms have the same charge as alpha, which is plus. And number 3, that they rebound because something is massive in the middle. Even though it's tiny, it's massive. I did this with my revision, so it's beryllium. So feel free to go through this at your own leisure. Now, I think this might come up as a 6-mark question. Because the gold leaf experiment has gone, alpha scattering is gone, they might reserve the 6-mark question for radiation. So I strongly recommend you know that radioactive atoms are unstable. Radioactive decay is random. Nuclear radiation is from the nucleus, and there's alpha, beta, and gamma. I strongly recommend you know what radioactivity means. Again, you can sort of pause this and have a think about the answers. You need to know it's in becquerels. Now, I recommend you know this. Okay, the symbols, the absorption, the thinnest material, and then you don't have to know the numbers at the end, but you have to know the symbols and the ionization density, it's called, so the most, the medium, and the lowest. Alpha and beta is alpha is a helium nuclei, beta is a fast electron. I would recommend knowing these definitions. There's a clear difference between irradiation and contamination. There's irradiation. Irradiation is when you're exposed to nuclear radiation. The body absorbs the energy from the radiation that can cause damage. If it's not too much damage, then the body can heal itself. If it's too much, where the body can't repair itself, that could be radiation sickness, radiation poisoning. If you've seen the Chernobyl series, it depicts that rather graphically, but really well. Contamination is where, so radiation when you're exposed to radiation. Contamination is when the actual metal dust, the fine particles of radioactive material, is on your skin or inside the body. If you breathe it in, if you ingest it by eating it, then it's inside there. It can travel through the blood to your cells and get into the cells. The little metal dust particles and the little bits of metal give off alpha, beta, and gamma. The cell nucleus can be mutated. The DNA can change. The cells copy themselves through mitosis incorrectly. And that sadly is what cancer is. It's a mutation. Okay. And there's a question there about half-life. I strongly recommend you know this as well. Half-life is the time it takes for radioactivity to lose half of its radioactivity or to have the number of radionuclei. You need to know it in terms of graph format as well. Have a look at that at your own time. You have to know how to calculate half-life in terms of a numerical question. I strongly recommend that you put down the word start to begin with. There is an equation which I don't want to cover it because if you're not competent in maths, it will just make it look hellish. I recommend put down the start, and then you take the number of half-lives from there, and then for this question example, you work out the number of half-lives that go from 4800 to 150. 5 half-lives takes up 20 years. A half-life is an exact division of the time. So we get 5 half-lives in 20 years. 1 half-life will be an exact division of that, which is 4 years. Here's some other ones you can look at in your leisure. There's a more problem-solving one when you're given a medical example, or when you can safely use a gamma tracer. So you have to apply the same principles, but again, the word start is there. I recommend knowing this. Now, you don't have to look up the table. You have to be able to know the numbers. Now, you need to know the numbers for helium and, for alpha and for beta. And so this question here, if you know the numbers for helium is 4 and 2, and you know the numbers for beta is 0 and -1, then you can, the rest of the numbers just follow on. Now you might get 3 marks for these questions. They're pretty mark dense. You get a lot of marks for not a lot of work. You have to know the values. How can polonium-210 change to 206? By emitting 1 alpha and 2 betas. So you've got to be comfortable doing these nuclear decay equations. This is triple. You don't have to know this one. And that's triple as well. So we are not knowing this one. And there we go. So please, if you want to download if you want to download that little file, you can do. Just one tiny little thing, because people always get confused with this, is beta decay. If we've got a nucleus of let's just, we got that there, and we've got now the dark circles are protons. Let's do one more. So we've got 4 protons, and we've got 1 2 3 4 5 6 neutrons. That's going to be 10 mass in total. Now what happens is, in beta decay, in fact, let me just put that in there. So we've got 1 2 3 4 protons, 1 2 3 4 5 6 neutrons. In beta decay, one of my neutrons changes to become a proton. Okay, and it does that by firing out a beta particle. And so this neutron, so remember, these are the protons, these are the neutrons. This neutron becomes a proton. So now my numbers are going to be 5 protons, and I've now got 5 neutrons, but I've still got 10 mass. And so beta decay, that's why there's a 0 at the top, because you don't lose any mass, but you do gain a proton, because a neutron has switched to become a proton. So chemically, we're now a new atom, because we've now got 1 extra proton, but because we've lost a neutron and gained a proton, we've still got the same mass at the end. That's where beta decay comes from. Okay, so I think I'll leave it there. I don't think I have anything left on the browser or the PowerPoint. Let me just check there. No, I don't. This one, just really quick of this one here, is a little simulation I made up to show that radioactivity is random, but if you take enough of a random event, it can be predictable. For example, if I roll a dice 10 times, then that's the breakdown of the rolls of the dice. If I increase the rolls to 100, then 1,000, 4,000, 20,000, you see that the graph begins to flatten out, and that there's little variation in the numbers of 1, 2, 3, 4, 5, 6. To the extent where if I take 1.2 million dice rolls, I'm pretty much guaranteed a consistent number of 1s, 2s, 3s, 4, 5s, and 6s. So if we take this 2.4 million, and yes, I did, there's 2.4 million cells filled in there. If we take a random process, if we take enough of them, they're no longer random. Individually they're random, but together they are predictable. So I know that 2.4 million rolls of the dice is going to produce randomly similar numbers for 1s, 2s, 3s, 4, 5s, and 6s. That's where half-life is predictable. A random process over 1 or 2 atoms, taken over the course of several billion atoms, becomes predictable. So that's why half-life of a material is fixed. Okay, it's a set time period. Okay, I am going to leave it there, folks. The kickoff started 50 minutes ago. Please go back and watch this if you're stuck with anything. Have a look at the circuits video. and good luck tomorrow morning. I ask your teachers if you're